All right, so this one says Ted is traveling on his railroad car with a speed of 95% of the speed of light relative to Alice. Now, Alice measures the time required for her heart to beat 85 times, and she measures an elapsed time of 62 seconds on her watch for this event. So it's saying who can measure the proper time, Ted or Alice? And the answer to that is Alice measures the proper time of her own heartbeat because it's in her own reference frame. So yeah, last time I gave a couple examples about the difference between proper time and dilated time when it came to relativity, right? So we use the symbol T or TO to represent proper time. And then we use the symbol T prime to represent what would be a dilated time. And that's the relativistic phenomenon that we see with time, is that it can be stretched but never shrunk. So it's sometimes helpful to think of the proper time as like the shortest time, the shortest possible time for an event to take place. And then, of course, the dilated time is a stretched time. Last time I said that there was a relationship between dilated time and proper time. And that relationship is T prime equals gamma times the proper time. All right, so gamma has a formula. 1 over the square root of 1 minus v squared over c squared, where v represents the speed of one reference frame relative to another. And so Ted has his own what's called reference frame that's moving. Okay, so Ted, his frame, is headed to the right with 95% of the speed of light. But Alice has her own frame stationary on Earth. Now, one of these frames can be called S, and one can be S prime. All right, so S is like the stationary frame, and S prime is like a different inertial reference frame which is moving relative to S. So notice that Alice is at rest relative to herself, which means that she can measure the proper time of her heartbeat. She's going to call it TO, which is the proper time, 62 seconds for the 85 beats. This is proper time for that event. Now, keep in mind that the event is 85 beats. Now, it asks how much time elapses on Ted's watch during this same motion. So we know on Alice's watch it's 62 seconds. But because of relativity, Ted would not measure that same time for the events. And that's what's different between classical physics and Einstein's physics here, is that in classical physics, the time between two events would have been assumed to be the same. So we have to calculate gamma. So we'll put in the speed that Ted's cart is moving here relative to Alice. And we can just put it in that form and then divide by c squared. As you can see, the c's are going to cancel. Let's see what we get for that. All right, I'm getting a gamma of 3.2, which is a fairly large value. As we said before, 1 would be the minimum for gamma. 3.2 is pretty significant because of the high speed that Ted is moving. So now we just want to take that gamma and plug it in here, and we can solve for t prime. I get 199 seconds as measured by Ted. As you can see, it is a dilated time. It's a longer time than Alice would have measured.